interesting and clever. So think about that as they go. All right, the first one up is Kayleen Stocking from UC Berkeley. Kayleen.
All right, thank you all for being here bright and early. So I'm going to be talking about work with my collaborators, Alison Gopnik and Claire Tomlin. And the title of my talk is From Robot Learning to Robot Understanding, which is a little bit ambitious, but hopefully over the next few minutes, I can convince you that maybe there is in fact something sort of to this. So consider this situation where you have a little pizza delivery robot that is trying to deliver some pizza by rolling along the sidewalk towards the top of the screen. Now, if you live in an area where these robots are common, you may have heard the rumor that they are in fact teleoperated by humans. So imagine for a second that you are a human in charge of controlling this robot and getting it to its destination. Now, when you encounter this situation, you need to be able to safely navigate around pedestrians. And looking in this particular case, you can see that this human is standing by a bus stop. And so it's quite reasonable to infer that they're probably waiting for a bus. And since there's no bus in sight, they're probably not going to move anywhere. And so it does seem like it is, in fact, probably safe to go ahead and pass this pedestrian on the sidewalk. But we can also consider this alternative situation where there's a soccer ball on the other side of the sidewalk. And in this case, a quite reasonable hypothesis that sort of seems to come to mind is that maybe the human just dropped or kicked this soccer ball, and therefore they might be about to run across the sidewalk to go retrieve it. And so in this case, we want to be a little bit more cautious about continuing to go forward in this situation. And so that's sort of our reasonable conclusion here. Now, what we really want is for this robot to be autonomous and to make this kind of decision on its own. But looking at these two figures, we can imagine that the appearance of the human might be quite similar in these two cases. And so a good question is, like, how does the robot disambiguate between these two scenarios and figure out which of these is safe and which is not? And we can imagine that especially for these more rare edge cases, especially like the soccer ball situation, we might not have data in our training distribution that this robot has seen before that it can leverage to figure out that this situation is unsafe. And even though you have probably never been in this exact situation, you can probably still come to the conclusion that the soccer ball situation warrants extra caution. And so somehow we're able to do this without having seen this prior exact situation before. So how can we give this ability to the robot? Well, if just doing deep learning isn't good enough, we might think that maybe a model can help instead. So for a model to be useful in this situation, I think there are a few different criteria that we would like it to fulfill. So first of all, it should be able to represent the relationships between objects, such as between the human and the soccer ball. It should be able to predict future states of the scenario, contingent on how the robot is interacting with the world. It should be able to handle the uncertainty and dynamicism inherent to interacting with the real world. And finally, it should be able to support online inference so that it can really operate in real time. And so I think that there is actually a kind of model that might fulfill all of these criteria, and that's the causal graphical model. So just to give a brief overview of how these work, we can assign each object or variable in this scene a node in a causal graph. And each of these nodes is going to be associated with some probability distribution over possible values it can take on. So in this example, we might have a hypothesis that the human is waiting for the bus or that they are playing with a ball. And so these can be our two different values. And then finally, we're going to have causal relationships between each pair of nodes. And this is going to tell us how the probability distribution of one variable is going to be affected by the value of other variables. And these relationships between nodes is really what's going to allow us to perform inference and to make good predictions about novel situations. So returning to our motivating example, if we observe the human by the bus stop, and we have these two candidate models that I have here below, the one on the left is representing a human waiting for a bus, and the one on the right is representing a human playing with a soccer ball. And if we have these two candidate models, we can sort of use the evidence from the scene, namely the fact that there is a bus stop there and not a soccer ball, to realize that the model on the left is in fact a lot better description of this scene. And furthermore, we can use the relationships encoded in this model to infer that because the human is not very likely to run across the sidewalk, it is in fact probably going to be safe to pass them. And we can do a similar procedure with the soccer ball situation where we can infer that the model on the right is a better fit and that furthermore, we need to be a little bit more careful about continuing to go forward. This sort of begs the question, however, like even if we can do this inference and get really good predictions, we need to have these good candidate models before we can do this procedure. And this is really the key question, where do these models come from? And this has been called a lot of different things by different people. For example, it's been called the frame problem by the philosopher Hubert Dreyfus. And, we can take, but all is not lost because we can take inspiration from emerging ideas from cognitive science about how humans are able to solve this problem. So for example, one possibility is that if we represent the space of all possible models for a particular situation, the process of choosing candidate models could be considered a stochastic search problem. And we could do better at this stochastic search, for example, by learning prior distributions that might be conditioned on things like the current task that we're trying to execute or the current setting. Once we've drawn candidate models from this stochastic search space, we might also want to be able to refine them. And for this, we might be able to take inspiration from things like how humans intentionally improve our hypotheses by doing things like trying to make them simpler or more accurate. And so these gives us some ideas of how we might be able to do this. Now, even though we have some ideas, this might all seem quite, vague and difficult to you, and that probably because it is quite vague and difficult. But I want to take the last few moments to try and convince you that this is a good idea, even though it's quite difficult. So we know that interaction with the world is really critical for learning, and specifically learning for both animals and robots. And this is something that we have leveraged in reinforcement learning. But reinforcement learning only gives you causal information with respect to a particular reward function. And a really key hallmark of human intelligence and human learning is that we are able to take causal information that we've learned while performing one task and flexibly apply it to other tasks that have nothing to do with what we were doing before. And causal theories appear to be a really key part of how we are in fact able to do this. And so I think that this really presents a really wonderful opportunity for emerging research in cognitive science and how the human mind works to help inform better algorithms for robots to sort of be able to leverage these same kinds of abilities. And furthermore, for the tasks and platforms of robotics to help test and refine our theories about how human causal modeling works. So my hope is that by sort of leveraging this virtuous cycle, we will in fact be able to transition at least a little bit from robots that learn to robots that understand. Thank you.
And next we're going to bring up Victoria Dean from Carnegie Mellon.
Hello, I'm Victoria, and I'm here to talk about Robots on Demand, our vision for a democratized robotics research cloud, with Yo Shavit and my advisor Abhinav Gupta at Carnegie Mellon's Robotics Institute. Gonna need the clicker for this. Imagine someone trying to get started in robotics research. First, she has to obtain a robot. Then she tries to set up ROS, but the networking's a mess. After days of trying to get libraries to play nicely with each other, she finally sets up the software infrastructure. But she doesn't have a task. After picking all of the sets of objects to grasp and tuning the success metrics, she's finally completed all the setup just to start her project. Unfortunately for her, her method turns out to require millions of samples. And that's not including the baselines she has to recreate. Back to simulation she goes. Meanwhile, the computer vision researcher has written 3 papers in time to submit to CVPR next week. How does he do it? He uses a GPU cluster with an easy interface for parallelizing experiments. He has software tools and open source baselines that make it easy to get started. And last but not least, he has access to large-scale datasets. The vision researcher is free to focus on developing new algorithms rather than the extraneous work that the robotics researcher is still stuck on. So the question is, how can we make research on real robots as easy as computer vision is? Enter the Robotics Research Cloud, a physical center filled with real robots in which a researcher can remotely submit experiments that will run on these robots. Common tasks and environments act as benchmarks, and all of the experiment data is open sourced. We've seen all of these components in prior efforts, but we need to put them all together at scale. With the Robotics Research Cloud, the field will look pretty different. Research won't be limited to those with robotics expertise and the resources to afford real robots. An ML researcher with no hardware experience could conduct real-world experiments, or even a high school student could participate. All Coral submissions will have experiments on real robots, so we won't have to debate whether to reject a paper because they didn't have real-world results. And finally, when everyone has access to the same hardware, anyone can show that their method is the best. Labs with the most resources won't just have state-of-the-art results because they had the best robots to train on. A number of questions remain which will guide the design of such a cloud. First, we'll have to pick the robots. We could use off-the-shelf robot arms, though these might become obsolete over time. We could also use more forward-looking technologies like hands or soft robots, which would allow hardware researchers to have a real experimental testbed. Next, we'll need to pick which kind of tasks to use as benchmarks. They should allow for autonomous resets and evaluation, and possible manipulation tasks would be pouring, scooping, or writing. The level of abstraction will change the user interface and experience. So giving more direct access allows for flexibility, but the lack of constraints could lead to safety issues. Next, do we need teleoperation for trying out tasks or collecting demonstrations? Having real-time remote teleoperation might require more engineering investment. Finally, this will be an expensive effort, which will require combining multiple funding sources. We've seen interest from both government and industry sources, and we're actively pursuing both. So let's say that we can get good answers to all of these open questions. Then we can look at a timeline for scaling up the first robotics cloud center in the next 5 years. The initial work is in developing infrastructure, which we're actually already doing. With seed funding from Schmidt Futures, we're creating a remotely operable robot interface. Next, we'll need to scale up the robots. We'll decide on and acquire the relevant hardware by next fall. By spring 2023, the robots are assembled and available for remote access by a select set of labs, and their experiments will inaugurate the open source dataset. That summer, the center will begin operations with the experiment queue open to the larger community. The following 2 years of use with 100 robots will lead to 400,000 robot hours. If we estimate that a robotics paper takes 100 robot hours worth of experiments, then this would lead to 4,000 papers by 2025. As you can see, the robotics research cloud holds a lot of promise and also asks a lot of questions. If you have thoughts, we'd love to hear from you during Q&A. You can also visit roboticscloud.org to get involved or email us directly. We look forward to making this dream a reality with help from all of you. Thanks.
Martin Riedmüller from DeepMind, who's going to give us another entry into the competition of what is the common denominator. Martin.
So welcome everybody. I'm going to talk about collect and infer, which hopefully gives us a fresh look on data efficient reinforcement learning. And this is joint work with my co-authors, Toby Springberg, Roland Hafner, and Niklas Hayes. And also a lot of discussion with my team and other colleagues at DeepMind has gone into this work. So reinforcement learning is becoming more and more important in robotic control. There's famous work by Sergey Levin, for example, in Google about the arm farm, famous sim2real work by OpenAI, very impressive hand manipulation of a hand, and also learning from scratch, which we are pursuing in our team. But all these work have in common that data efficiency is really a key ingredient to make reinforcement learning work in the real world. So the classical reinforcement learning work doesn't care too much about data efficiency. So data comes in, transition comes in, the policy is updated, the new policy is applied to the plant, and the data is basically thrown away. This changed by the introduction of an actual memory that stores all the transitions and reuses those, which make the whole reinforcement learning process much more data efficient. And the FITQ or the neural FITQ algorithms are example of this. And collect and infer is basically a continuation of that work that puts this to the extreme and really asks for reinforcement learning that is most data efficient, as data efficient as it could be. So, and it basically proposes to see reinforcement learning as two distinct but interconnected processes. One is to collect the data with the question, what data collect to make the most learning progress? And the other question is, if we have some data, how can we infer the most knowledge out of it? How can we squeeze everything out of a data source? So basically, this splits this overall agent in two distinct processes. And one of the big advantages now is that we can have clear metrics to optimize each of these two processes separately. For the inference, the question is, given a fixed batch of data, what is the best learning algorithm to get the best policy out of this? And there's already a lot of research going on in this direction. And on the other side, the collection question, which is not so much investigated, but should be much more. Namely, if we have a fixed data budget, what is the right way to collect the data so that an inference algorithm can get the most out of that data? I just want to quickly refer to some research that is already done here. I don't want to go into that table, but the thing here is you have a fixed data set and the different learning algorithms come up with very different qualities of the policies that you see reflected in the very different numbers here. So the inference algorithm that works on the data really matters a lot. And also the same is true for the collection. The question is, what is the right way to collect the data? And here we have a similar experiment. So we have, again, a fixed data budget. The learning algorithm, the inference algorithm is also fixed, but only the collection, the data collection procedure changes. And as you see at the bars over here, the quality of the resulting policy changes dramatically with a difference in the collection policy. So that is recent work of our intern, Will Whitney, but there's also a lot of other work which is referenced in the paper. There's also already an agent architecture that lives to that idea, which is called scheduled auxiliary control. And the idea is basically that you have a lot of skills that are available to the agent, and the scheduler selects what skill to apply next in order to collect the best data for the learning procedure. And again, there's also an inference procedure that tries to get out the best of the data by using relabeling, for example, and other means to squeeze out the best of the data. And the suggestion would be that going forward, we not only think in reinforcement learning for policies, but also think in learning models, learning statistics, learning new reward functions, so everything can be learned out of the data and then used to make the agent even more efficient in the collection process. And this also lives in the spirit a bit like Rich Sutton and colleagues already have proposed 10 years ago with a hard architecture to transform experience into knowledge. So collect and infer. It hopefully inspires novel ways how to optimize, evaluate, and improve these two parts, namely collection and batch reinforcement learning, which has already started but can be improved a lot. And it also gives a blueprint for the design of new future agent that hopefully much more data efficient and then also apply to a lot of even more interesting robotic domains. And there are many further interesting research directions around these topics, hopefully inspired by this framework, and hopefully this framework helps to give a clear direction for future research that you can also find in the paper. Thank you.
Good. Can you give him
That's the speaker, Eli Aljon-Boots, who's going to talk on dual arm adversarial robot learning. The floor is yours.
Okay, perfect. Hello, everyone. I'm very glad to be able to present to you dual arm adversarial robot learning. So when we talk about our robot learning work, we often focus on concepts, algorithms, theories, systems, implementations, and so on and so forth. But what we usually fail to mention are all the human and engineering details or efforts actually that are needed to run such experiments. And for instance, randomizing the state of the environment or objects in the environment. So let's say the robot is trying to learn to perform a peg and hole task. Ideally, you would want the hole to be at random different poses at the beginning of each episode. So how do you do that? A similar but more general concept is the environment reset mechanism. So at the beginning of each trial, you would want to reset the robot and everything related to the task to a certain initial position. And here you might face problems like objects being stuck, like a peg stuck in a hole, or obstacles and similar. Another beast is like the reward computation. So how can you actually obtain the reward? You need access to the states of every object or every entity related to the task. And of course, safety itself is a big problem. So of course, in simulation, this is very simple. So as you can see in the snippet of code on the right, that's all handled. But in reality, that's not the case. So what we ideally would want to have is actually the capability to run long-term experiments and forget about them. But what we usually have is a human in the loop, typically a PhD student hanging around the lab, moving objects around, resetting the environment, pushing the robot, and keeping a hand on the safety button. So can we get rid of, or at least reduce the need of human in the loop during robot learning, specifically for manipulation? And this is what I talk about in this paper. So what if we actually try to replace this human in the loop with another robot, because that solves everything, and try to formulate the whole problem as a joint optimization problem. And of course, I talk about details of maybe how to do that in the paper. But in a nutshell, what we end up having is like two robots, a trainee trying to perform the task by trial and error or anything. And then the trainer robot, which here plays the role of a human. So it resets the environment, whether in a predefined way or a simultaneously learned way. This could also be adversarial. It could also apply adversarial actions during the learning process of the trainee. And this could be based, for instance, on adversarial reinforcement learning from Pinto et al. And many other things to support the whole process. So what do we actually gain out of this? So hopefully that's a step towards more autonomous experiments. For instance, if we revisit the peg and hole example, and now the hole could be assembled to the end effector of the trainer robot. And you could easily reset the environment, randomize the position, all kinds of things. And because you have access to the state or the whereabouts of this object, the hole in that case, or an object if you're doing pick and place, it's easy to design safety mechanisms to collect data for robot supervised learning. So for instance, since you know where the objects are, you could collect data sets of, let's say, images and whereabouts or poses of the object you want to manipulate, and use that to train your perception modules. Based on this knowledge, one could also design heuristic exploration policies to guide the exploration further. And another interesting aspect is, for instance, for human-robot interaction tasks, the trainer robot could simulate a human motion, and that's hard, but let's say it's possible, while the trainee tries to learn the HRI task, the corresponding one. What about challenges? So of course, we're adding another robot, so we're adding to the complexity. That's gonna be a problem by itself, and of course, we have to acknowledge that. We also have the additional cost to have the second robot maintain it and run the experiments. And of course, an interesting idea is, why just stop at one robot supporting? So why not more N robots? Of course, with only two robots, we might again fall into the same problems. Maybe the object is out of reach of all of both robots, and it's again impossible to reset the environment. So maybe scaling up might be the way. Now, in summary, whether based on the concept I proposed or what the previous speaker, specifically Victoria, proposed, I think we need a feasible real-world alternative to simulation for robot learning. Now, DARL, or the concept I just presented, is just one idea, but what else can you do? So I'm looking forward to discussions about the topic now or in the future. Thank you.
Okay, great. Can we bring everyone up onto the stage for the the adversarial part of this talk. No. Let's see. Jens, you're online. Can you hear us?
Yes.
Can we hear you? Okay, good. So I want to open it up for questions, and then we'll leave a little time at the end for the hypothesis about what's the common denominator. But Jens, do you want to go first?
Yes, so we have one online question for Kayleen by Sivan Zhuang. It seems that causal should be dynamic, otherwise a causal graph might be unreasonable in certain situations.
I'm not sure I heard the first part of that, but I caught that the causal model might be unreasonable in certain situations, and I think
should be dynamic. That was the
yes.
statement.
Yeah, so I think in the example I presented, it was like quite a static situation. And I think that might be, I guess, like the easiest kind of situation to tackle first. And I think that there is some sort of situations where that could be quite useful. But I definitely agree that in order to get this to work more broadly, we would need to somehow incorporate dynamics into the model, and potentially things like factor graphs, I think, could be a useful inspiration for how we might be able to accomplish that. But I think there's a lot of sort of ground that would need to be covered there.
Great, thank you. And question, yes.
Question for Martin. So I like the appeal of this collect and infer framework. It kind of reminds me loosely of like ADMM methods and minimax optimization that we see in like GAN literature. But simultaneously, there's this kind of alternate perspective to GANs, which is based on just like minimizing F divergences instead of this kind of dual optimization process. So what are your thoughts on like that in the collect and infer framework?
Yeah, I think that is something that we really should tackle in future research. So the current collect and infer is basically just making aware that there are these two optimization processes and that they should be combined. And I think, as you mentioned, there are very different ways how to implement this optimization as a dual optimization or as something being more competitive. But this is really something that is completely open to future research.
Yes, right in the...
Hi, it's for Victoria. Will the data that are collected and sent by the robot, the actions and observations so on, be made public, like as opposed to siloed per user?
Yeah, absolutely. We'll have a shared data set with all of the experiments run by anyone.
Good, okay, right over here, there's a question. Do you have your hand up over there? You're next, too.
Hey, Victoria, this is a question for you. So, there's a big aspect to having a robot farm, which is maintenance, and, robots drift at different rates. Do you have any thoughts on how you would do this reliably and evaluate reliably?
Yeah, absolutely. So there's, I guess, a couple parts to that. There's staffing, which might involve things like putting objects back when the robot throws them or something like that, and also more hardware maintenance when motors fail and that kind of thing. For the hardware maintenance, the hope would be that since we have a large collection of robots that are copies of each other, then we could have some deal with the manufacturer where they might provide help with that. For the other part of staffing, yeah, we'll definitely need staff for the center, and that's something we've factored into the plans.
Hey, another question for Victoria. Sorry to throw it all at you at once. I really like the idea for the robotics cloud. I'm wondering how you're feeling about kind of the saturation problem as we kind of go through your timeline. We collect, thousands upon thousands of hours of robot data on these, single robots on these single workspaces. What is your vision for scaling up beyond that, beyond the tasks that you can kind of see on this fixed workspace?
Yeah, absolutely. You're totally right that we will have saturation. So if we have 3 initial benchmark tasks, then I think the goal of any benchmark is you start out with not great performance and then you saturate it and then you move on to harder benchmarks. So we would add new tasks and also new hardware and environments over time. And I think this would be pretty easy to swap out because the the capital costs of the robot hardware and sensors and that kind of thing are not actually that large compared to the infrastructure and staffing needs.
This is a question for Kayleen. So one aspect of the human tendency to look for causality is that we also over-find causality and get like pseudoscience and fake placebo effects and things like that. You know, it's kind of out there, but do you think there's some way of, is this inherent? Do we need to do this over causality in order to be intelligent in other ways? Or do you think there's some way of not straying too far in that direction for robots?
Wow, that's a really interesting question. To be honest, I haven't considered it. My guess is that you wouldn't be just using causal modeling to try and plan your actions. And so, you know, maybe if you're selective about the kinds of situations you're applying it in, or, you know, like waiting until you have a certain amount of data where you feel confident about being able to make that causal prediction, you might be able to get around some of those sort of effects that you're talking about. But honestly, I think that's really interesting, and I need to think about that more. So thank you for bringing that up.
Great, thank you. And so on that, just following up on that, I mean, something I noticed is that there's a fair amount of commonality between Victoria and Ellie's talks, and the commonality between you, Kayleen, and Martin is sort of that you're coming from very different. You know, you guys are almost at the opposite of each other. I mean, in that Martin is very confident that RL is the answer, and we just need to get more efficient data collection and inference methods. But you're saying actually there's something more that we can't get from RLs. Can you say more about that? I mean, this theory of mind and the interrelationships between people seems very, very subtle. I mean, because if you imagine rather than a soccer ball, it's another person. If you're looking at those two people, you're trying to infer what is their relationship. And you think about that is so subtle, right? Are they friends? Are they enemies? Are they, you know, do they know each other? Are they just two people having an argument and ignoring each other for the moment? You know, there's so much to read into that. And it seems like that's going to be very hard from any RL kind of scenario. So what are your thoughts on what, is there something that's missing from RL?
Yeah, so I guess sort of my take on this is that I don't think that there is anything that is impossible to do with RL that is magically made possible by the kinds of models that I was sort of proposing. But I do think that because they sort of allow you to use your knowledge about pairs of objects and sort of compose them using a graph into a new situation, that allows you to deal with edge cases that you haven't seen before. And so I think this is like something that we've seen in autonomous driving, that one of the like main challenges to getting autonomous vehicles to work in the real world is just this process of like trying to deal with as many edge cases as possible to be able to get above like some threshold of you know, acceptable safety. And my sort of what I'm arguing for is that I think that using something like causal modeling could help us deal with a lot of those edge cases with much less data than we would require if we were purely using a deep RL type approach or a model-free RL approach. But I'm not trying to say that like I think we should get rid of RL entirely to replace it with something like causal modeling. I think I'm trying to say that, you know, perhaps this is something that is worth looking into as a way to, you know, perhaps do like a type of model-based reinforcement learning or something to like use as a safety backup or something like that.
Okay, very diplomatic. All right, Martin, why is everything that Kayleen said total rubbish?
I just wanted to start with saying thank her for making the bridge to reinforcement learning. And I think she's absolutely right. While I believe that finally policy should be really learned from data, so basically it should be derived model-free because the data is actually the ground truth that we get from the world. I think having models within the agent absolutely makes sense, for example, to do better exploration. Because in her example, when you want to get across on the sideway, and you already have a model that predicts you cannot go there without hurting the human, so this is probably a bad idea, then why should you try to bother to explore dumbly? So you should use, of course, that knowledge. And the second last slide that I proposed actually advocates for being much more general with the knowledge that we generate from the experience. So having models and also inferring knowledge from these models to do better data collection and avoiding obvious mistake. That's definitely something that I would like to integrate in my research if she produces the results.
Okay, very good, very diplomatic too. So, you know, it seems like this is almost another category of these trolley problems. I mean, in some sense, what you pose there is trying to understand, is it safe to go, and understanding this relationship. And as you said, it may be a binary, but it may be many more multifold than that. And I'm just curious if everyone can talk about that aspect of what's not in that data. I mean, it seems that there's so many nuances to all the relationships that can happen. And in some way, the way we learn about relationships is by obviously interacting, but also through reading books and watching movies and everything else, right? We're constantly studying these things. My daughter reads these young adult novels, and that's how she learns about romance and interactions, right? Which are so nuanced and important. Now, here's a question, so that in some sense, you have to feel the emotions in order to be able to process them and sort of infer them. It's kind of an empathy that goes on, would you say? Now, we know that robots so far don't have emotions. Do you think that we need some model of emotional model, some effective model to work in the world? I mean, that's kind of what you're proposing in a very practical way. Is it safe to go forward? Well, I have to understand the emotions between these two people. Martin's handing that off. Okay.
Yeah, that's a really interesting way of putting it. I guess maybe this doesn't fully answer your question, but I think that when we're doing model-free reinforcement learning, that sort of like judgment about what the right thing to do is, like that moral or emotional judgment, is currently being like distilled into the reward function. And that's sort of this kind of black box thing there. You know, I think it's well understood that we're very bad at predicting what kinds of behaviors a particular reward function will actually lead to, especially in more complex settings. And so I guess using more explicit models doesn't free you from that responsibility to try and reason about or like think about the ramifications for what you're optimizing, but maybe it does make it a little more explicit and sort of like get past the stage where we just sort of sweep it under the rug into one reward function.
Great. Okay. Yeah, because I think that the data, right, what the state of the world, when you observe these two people, the same exact state could have so many different interpretations, whether it's safe or not. That depends on history and depends on body language and depends on just the look in the person's eyes, right? So it's really, there's something very subtle in that example, which I really like. Okay, so we have more questions coming in.
Can I ask a question?
Yes. Victoria, please ask a question of your
I have a
co-panel.
question that relates both of these two panelists.
Excellent.
Similar to the one you asked before.
Oh.
So Martine, it sounds like you were saying that causality could be used in the online data collection aspect, using a model for planning or something like that. But it seems like the causality aspect might actually be more useful in the offline RL setting, where the policy might actually be different from what's being used to collect the data. I'm curious what you think about causality in the infer step rather than the collect step.
That's a good question. I think that probably the inference mechanisms purely from data are probably already good enough without having an additional model, because a model would be only one way to kind of accelerate this process. So I'm not sure whether we actually need this in the inference process once we have good enough inference procedures. So I kind of really tend to believe that using models is something that you use while you're acting in the world, but the more you're acting, and it's probably, there's an analogy to humans. So if you're doing a new task, then you probably are using a model. How can I reach this object on the table? But once you did this 1,000 times, you stop thinking about this. So this is basically probably also something that Kahneman means with his system 1 and system 2 analogy. So I think, or I have the belief at the moment, that models are mostly useful for the data collection and for the behavior, for doing behaviors. But finally, if you collected enough data, then you should be good enough to go without a model for the inference process. But that's just a belief, and that's can be proven wrong, and can be absolutely right.
I guess just like pushing the analogy to human minds just a little bit further, I guess you could also make the argument that sleep seems to be pretty important, and maybe that is like sort of related to offline learning in some sense.
Ooh, good. Sleep. We haven't had that come up yet. The whole conference, actually, but that's great. So let me ask you a question. So Ellie, you and Victoria seem to agree quite a bit on the need for remote robots that can learn, or basically replacing the graduate student in the loop. What do you disagree with Victoria on?
Tough question. So I wouldn't say I disagree. So I think we're both trying to find feasible ways to make robot learning something feasible again. So what Victoria proposed is like a global, not just a global solution to everyone. So sharing an infrastructure, sharing data, which I think is great. But I guess at some point, although this is great, at some point there might be a limit to related to the question from one of the like previous question. So this might reach maybe at some point a certain limit. We might not be able to integrate more tasks, or we might say at some point, that's it, these are the tasks that our benchmark has. What I was proposing was rather like a local lab-wise solution to or like a alternative to simulation. So I wouldn't say that it's one or the other, rather the two.
Okay, Victoria, you want to rebut that?
Yeah, I think Ellie's right that the setup where you have an adversary could be really interesting. I think it would be harder to do this for benchmarks because every sort of individual experimenter would have different results because it's kind of a more non-stationary task. But yeah, I think I generally agree that autonomous, taking the grad student out of the loop is a good idea. One other difference would be whether we have one robot or two robots. So I think in my system, you would ideally just have one robot that's doing autonomous resets and evaluation and that kind of thing. And so I'd be curious what Ellie thinks about when we need one robot or we need two robots that are in different form factors or something like that.
Mm-hmm. Great. So it's a really nice idea because Ellie's really talking about the robots interacting. You were talking about all these robots in parallel in some ways. So he's trying to bring them together, which is really an interesting idea. Good. So we have time for one more question before we get to our final round. I'm going to give this to our fearless Ed Johns here because he's been working so hard.
Thanks, Ken. So I feel like one of the themes might be, do we focus on changing the hardware setup, or do we focus on changing the algorithms that are running on the robots? So I think that Kayleen and Ellie are advocating, well, let's change the hardware. Let's have lots and lots of robots together to collect data, or we have two robots doing dual manipulation. And then Kayleen and Martin are advocating, well, let's have better algorithms. How do we actually control those robots? So I'm wondering, like, what you guys think in terms of which of those is actually more important. So, for example, let's say we were to freeze the algorithms and only focus on building better hardware setups such that we could use those algorithms, or we freeze today's hardware setups and only focus on developing algorithms. And let's say you had 10 years of freezing one and developing the other. Which of those two methods do you think would result in the best policies in the next 10 years or so?
Ooh, good one. Okay, so you got one word answer here. You can either have algorithms or hardware advances in the next 10 years. What do you choose? Victoria?
Algorithms.
Okay. Martin?
Freeze the hardware.
Freeze the hardware. Okay.
Algorithms.
Okay, we are. And Ellie, are you there? What are you voting for?
I agree. Algorithms too, yeah.
Oh, everybody agrees. Okay. Too bad all you hardware makers. So let's see, any hypotheses about, and Jens, please jump in there. I'm happy if you have a question or anything you want to add right now before we wrap up.
We have a couple of questions for actually Victoria online. I'm just going to pick one that I find interesting by Jackie K from DeepMind. Can the robot cloud really be democratized when there are huge corporations with lots of resources contributing to robotics? Can the design of the challenge really be fair for all participants?
Yeah, I think that's a great question. One of the areas I'm pretty excited about is helping out lower resource labs. And so we would consider doing something like providing scholarships or support to maybe people at colleges that wouldn't ordinarily have robotics labs and that kind of thing. I think there's still some interesting interplay between companies that have a lot more resources and this cloud, whether that be if they're sponsoring the cloud, how does that affect their priority with the use of the resources or something like that. So I'm curious to hear if anyone has feedback, we can talk offline about that.
Great, thank you. All right, Jans, anything else from the online world? No, okay. So, all right, but how about in just we have like 60 seconds left. What do you see as common themes from all 4 talks? Anybody find anything? It's a challenge. Yes. Okay, good. Cooperative systems. Is that would you say it's fair that that's an element of your work? Kayleen? Yeah? Okay. Ellie? Would you agree that there's an element of cooperation that's in your...
Definitely. Yeah.
Definitely. Well, almost the opposite, right? But yeah, adversarial cooperation, yeah. No, it's true. I mean, that's right. So the interaction, right, between these systems. Excellent. What's your name? Eric. Eric's got the best suggestion so far. Anybody else? Common themes from online. How about, I'll throw one out, which is safety. That seems to have been something everybody talked about to some degree. Is that fair? Is it included? Martin, you had probably a little pinch less of safety, but everybody else talked about safety explicitly, but I thought you said something about safety in there, no?
It's important, of course.
Okay. Okay, with that strong endorsement, I think cooperation is on the lead here for the competition. Any other last-ditch theories that you want to put forward about common denominators here? You have one? Oh, good, okay.
I sort of noticed a theme of, whether we should be focusing on trying to get better, like standardized robot performance in the lab, or whether we should be trying to improve the capabilities of robots on complex real world situations. Mm-hmm. So maybe not like a unifying theme as much as like something that we all addressed, but came to different conclusions about the best way forward, I guess.
Good, excellent. Okay, so the difference between, let's say, very staged environments versus or common environments, right, versus real world messy environments that are also different. Very good. And that's right. So you and Victoria sort of disagree a little bit in some sense, because you're in favor of the real world. Yeah, the messy real world. All right, excellent. Okay, listen, thank you guys so much for being such good sports, for offering these great suggestions and ideas. Ellie, thank you for your great talk. Jens, thank you as well. And thanks from all of us.